Bosler. Thank you for the opportunity to present here today. I'll be presenting my work on Lagrangian particle methods for geophysical flow in the sphere. It's work that is supervised by my two advisors, Christian Jablonowski and Robert Krasny, and we are gratefully supported by a grant from NSF and one from ONR. The goal of my work has been to apply the techniques that have been developed in vortex methods to examine their application to problems associated with dynamical cores. So vortex methods are characterized by a Lagrangian representation of equations of motion and the use of the Biot-Savart law to solve for the velocity. They are typically associated with some sort of adaptive algorithm to maintain accuracy as the flow evolves, and they usually involve an integral which requires information about the global system, so we also want to examine ways that they can be parallelized so we can talk about the utility of them as far as the problems that are concerned with a workshop like this. My talk today is divided into two parts. In the first part, I'll go over the mathematics and the numerical method. In the second part, I'll show the results and talk about a remeshing strategy along with some adaptive refinement. To begin, I thought it might be good just to review the difference between the Eulerian and Lagrangian form. So here on the top line, we have the advection equation, and beneath it, the barotropic vorticity equation. One way to state the difference between the Eulerian and the Lagrangian form is in the Eulerian representation, you know where the grid points are, so you know position, and you're solving for the physical data, whether it's the tracer or the vorticity. In the Lagrangian form, you know the vorticity, or you know the tracer, and you need to find the physical position as a function of velocity and the physical data. There's advantages and disadvantages to both. The Eulerian grids, you know what their layout will look like in a computer ahead of time, so you can do a lot of calculations once, and they're straightforward to parallelize. But they have the disadvantage that you have to discretize the nonlinear advection operator. In Lagrangian form, the advective operator doesn't appear explicitly anymore because the material derivative becomes an ordinary time derivative in the Lagrangian form for motion following the flow. But we have the complication that the mesh distorts with time, and it's an irregular grid. The mathematical idea that makes Lagrangian representations possible is this notion of a flow map, which is defined by the equation in the box here. We have the Lagrangian parameter alpha, which you can think of like a label. We define it to be the initial position of fluid particles, and then we have the velocity and the physical position, which is given by the flow map x. For the advection equation, the flow map kind of is the advection equation. We have, for example, if we follow the test cases from the Luritzen GMDD article, we have a prescribed velocity and a prescribed tracer distribution. And for motion following the flow or for trajectories, which is what it's our job to solve for, the tracer concentration depends only on the initial position. So in the Lagrangian frame, we can treat the tracer concentrations per particle as a constant. And that's one of the nice advantages of the Lagrangian representation. In the barotropic vorticity equation, we have a little bit more work to do because we have to solve for the velocity ourselves. So for an incompressible fluid, we have a stream function, and we can relate the velocity to the vorticity through the Poisson problem. The Poisson problem can be solved with Green's function, and the Green's kernel can be differentiated to give a vector kernel for the Biot-Savart law. These Green's function kernels for the sphere were derived in papers by Bogomolov and Kimura and Okamoto, and they are the functions shown here. And what is important to us is that they give us the integral expression for the velocity as the convolution of the kernel k with the vorticity over the whole unit sphere. So to get the flow map for the barotropic vorticity equation, we substitute this integral for the velocity. And then because we solve the equations in the rotating frame, we have to update the vorticity by subtracting the material derivative of the Coriolis parameter. These equations have been studied by a large body of work by Drischel and Newton, along with Sakajo and Dr. Krasny's previous PhD student, Lei Wang. To discretize the flow map, which is the fundamental equation that we need to solve in the Lagrangian representation of motion, we cover the sphere in a series of particles and panels. Each particle, or each panel, has an active particle at its center, which we denote by the vector x, indexed by j, and then a series of passive particles at the panel vertices, here denoted by y. both sets of particles carry the data. They carry their Lagrangian parameter, they carry their tracer if it's an advection problem. If it's the vorticity equation, they carry the vorticity information. The reason we call the active particles active is because these grids we designed for the midpoint rule. So only the values of the vorticity or the tracer for the integral calculations at the panel centers are used, and the passive points are used for refinement and interpolation. We have to calculate the panel areas at every time step if the flow is divergent, and we calculate the areas by using decomposition into triangles, and the graphic looks similar for quadrilateral grids. There's just an extra triangle. But for non-divergent flows, we treat the areas as constant for the whole calculation. To complete the numerical method, we need to integrate in time. And so we have whatever velocity we're talking about, whether it's the advection case where there's a prescribed velocity, or whether it's the barotropic case where we have to solve that integral. And we integrate both sets of particles with fourth order Runge-Kutta. And we solve for the physical position as a function of the Lagrangian coordinate and time. I thought I should put up the discrete equations for the barotropic vorticity equation so you can see how the midpoint rule looks with those integrals. And we solve pretty much the same sum for the active particles and the passive particles. The difference is that the passive particles are advected by the active particles, and the active particles are advected by themselves. So these lead us to, when we have all this together, we can put our numerical method into motion. So here we have a Rossby-Harwitz wave with wave number 4. I chose the phase speed associated with the Harwitz paper so that the phase speed is 0. So we should see the red-blue pattern of vorticity remain constant. So even though the phase speed of the wave is constant, of course the particle velocities are not. So we should see the grid move with the motion induced by the vorticity. And we see nicely that the red and blue stay where they should, but we also immediately see a primary difficulty of Lagrangian methods, that the accuracy is going to degrade as the mesh distorts. So we've confronted this problem of mesh distortion for long times. It kind of puts a time limit on the calculations if you have no way to mitigate the problem of distortion. It can be appeased, I guess. It can be made better by increasing the resolution of your grid, but that can be an expensive way. It'd be nice if we could come up with a remeshing strategy that's appropriate to the problem size that we care about. And that brings us to part 2 of my presentation, where we're going to talk about the remeshing strategy that we've developed. I'll show results for the advection equation, which were just based on linear interpolation. And then for the barotropic vorticity equation, we upgraded to a cubic Hermite interpolation. And then I'll show some adaptive results, which are pretty new. So, as I mentioned, adaptive refinement has been associated with Lagrangian methods for a long time. The perhaps natural idea is to just simply divide a panel that stretches into smaller panels. And that's been done by Krasny's work with vortex sheet dynamics, which he also did with Feng in 2009. And it was also part of Lei Wan's thesis from a couple years ago. Drischel is well known for his contour surgery techniques, which address the same issue. And then, of course, there are semi-Lagrangian methods and ALE techniques that try to get the benefit of a Lagrangian representation without the problem of distortion. Our goal is a little bit different. We want to preserve the advantages that we keep in the Lagrangian form of the equation. So we need to obviously transfer the data from a distorted mesh to a regular mesh to maintain accuracy. But we want to do so in a way that keeps the advantages of the Lagrangian form of the equations. So our idea is to assign new physical positions that are associated with a regular mesh, and then interpolate the Lagrangian parameter so that we preserve the flow map throughout each remeshing step. So let's take a look at the Rossby-Harwitz wave that we just saw on the same mesh. It's the same problem, except now on the left-hand plot, I've plotted the initial latitude. It's the latitudinal component of the Lagrangian parameter. So the red and the yellow are particles that start in the northern hemisphere. The blue are particles that start in the southern hemisphere. And particles that start near the equator are black. And the idea is we let the problem evolve, but not too far. So the grid distorts, but not to the point where we lose accuracy. So at this point, we can still do accurate computations on the mesh. And at this point, we want to take what we have and move it to a new mesh. So we interpolate the Lagrangian parameter and put it on a new mesh. Now we've transferred the information that took particles from the poles in this region toward the equator and particles from the equator toward the poles in this region, but we've put it on a mesh that's nice and regular and accurate again. And then to assign the problem data, we take advantage of the fact that materially conserved quantities depend only on this Lagrangian parameter. So we simply assign either the absolute vorticity or the tracer concentration based on what we just interpolated. This is exactly what we did for the results for the advection test cases, for the deformational test cases. Here we have the slotted cylinder test case. We did this with linear interpolation only, and we still got nearly quadratic convergence in the mesh size for 400 time steps throughout the calculation, remeshing every 20th time step. And notably, this technique doesn't introduce any oscillations or overshoots, and it preserves tracer correlations exactly. So we are pretty happy that a midpoint rule and linear interpolation could do this well. And then moving on to the barotropic vorticity equation, in addition to Rossby-Horowitz waves, we've also been looking at a single Gaussian vortex. Here we've put it just north of the equator, and I put a coarse mesh on there so that underneath the green grid lines you can see the initial latitude that we've been looking at for the last couple of slides. And these were remeshed every 40 time steps. And you can see the remeshing work, and the grid snaps back to a nice distribution. What's nice about this is that the roll-up of the vorticity underneath the grid lines evolves smoothly. So we feel like this does a pretty good job. But we got remeshing at least figured out good enough for where we are now. We see a problem develop later that's not associated with remeshing or distortion. Now the filament has evolved to the point where it's thinner than the grid panels. And so now we have this problem of the vortex has shed a filament that is skinnier than we can resolve, and this secondary vortex that develops from the filament we're pretty skeptical of because that resolution is very coarse. So to get an idea of what that does over a longer time, we run the same computation on a 1-degree mesh where there's too many grid cells to plot. So here's the same vortex on a 1-degree mesh, which is about 80,000 triangular panels. And we see that the filament that develops is indeed dependent on the grid size. This filament will take longer to appear, and the vortex that develops is much smaller and weaker than the one we just saw in the coarse mesh. We do see a strong vorticity front develop because the particles that started near the equator were transported poleward. So they started with an almost zero Coriolis parameter, but to conserve their absolute vorticity, when they move into a region of positive Coriolis, because they move into the northern hemisphere, they have to develop negative relative vorticity to conserve the absolute vorticity. So here we look at the same exact simulation, but from a different angle so that you can see the small scale features that develop inside the vortex core, because that's another region we want to focus on. Our goal is to resolve vortex cores and filaments, and we'll talk more about that as we go. So the increased resolution and the remeshing have brought us a way to increase the time for which our calculations are valid, but we still have this problem of eventually the filament gets down to grid size or smaller, and what should we do there? And that leads us to the adaptive refinement ideas. So our goal, just like the rest of us, or everybody that does adaptive refinement, is to resolve small-scale features as they evolve at minimal cost. And again, we've used the Hermite interpolations for this iteration of our code, and we use the ones prescribed by Renka and the software package that accompanies his papers. Our criteria for adaptive panel refinement, we use 2 of them. The first one is the magnitude of the relative vorticity multiplied by the panel area. So you can think of that as the absolute value of the circulation around a panel, and that's designed to target a vortex core. So when we run that criteria, we get good resolution wherever there's a lot of vorticity. And the second criteria that we use is inspired by the simulations we just saw. In order to resolve those filaments, we note that they show up where there's been there's a large change over a small area in that Lagrangian parameter. So the second criteria we use is this total variation idea of that Lagrangian coordinate. And that is designed to target filaments. So we can run that simulation again with these adaptive criteria. And it starts out, we get a nice resolution in the core. And then the filament starts going, and the grid picks up those two. But even these tolerances aren't small enough to get the filament all the way through to the end, as we see if we look at it from the other angle. We'll see the same problem, and that's because we haven't chosen tolerances that are small enough. But at this point, we just wanted to see if these criteria would do what they want, and they appear to be doing their job pretty well. We get good resolution in the vortex cores and the filaments until even these tolerances are too large for the problem that develops. So the grid looks well resolved on the right-hand plot, but on the left-hand plot, we get this checkerboard pattern, which appears at every remeshing, which I think is error. And what I think it is that we have a really well-resolved flow map now, but we're still using the midpoint. And so we're trying to assign one constant value over a whole panel, and it's trying to pick out one of those where there's a lot of change in the Lagrangian parameter. So we need to increase our quadrature scheme or improve our quadrature scheme to move further. But before we talk about what else we need to do, I thought it would be good to compare the adaptive simulation we just saw to the 1-degree uniform resolution we saw at the beginning. So here's a 2.5 time calculation with 12,000 panels in the adaptive mesh. And you can see that the resolution is highest in the core and the filament. And we compare that to the same time on the uniform mesh, and they compare very well. So we're pretty happy with these criteria, but we need to get better at choosing the tolerances to best get the features resolved that we want for long times. A quick note on parallel timing. You have to do the global sum for each particle, but each particle can be integrated independently of every other. So that's very easy to parallelize. And just parallelizing that integral of the velocity and none of the other parts of our code, we get linear speed up for the number of processors that I have access to. The parallel scaling is better for larger problem sizes. And so here you see a 2-degree mesh simulation scales up to nearly 90% efficiency on 25 processors. And the adaptive code scales less well because it's a smaller problem size, but it's a notable decrease in wall time, which you'd expect. That's about the end of my talk. I just have one more slide after this one. We talked about the Lagrangian representation and how you do that with the flow map. We did the Green's function and the Biot-Savart law, and the remeshing strategies and the refinement criteria. For our next steps, right now we want to increase or improve the quadrature scheme. And our first try is to do it with the data that we already have. We already have data at every one of the passive particles, but we're assigning the midpoint rule, so just the value for each panel is just the value at the center. So we can increase to a linear representation using the data that we already have. And then we're trying to figure out another way to increase to even higher order quadrature, but that work's ongoing. The next thing we're probably going to do with the code is implement a tree code algorithm, which reduces the velocity integrals to n log n complexity and a significant time savings. And then we have a few ideas. We think this method would work very well with some Voronoi meshes, so we started working on that too, but I don't have any results to show for it yet. And then, of course, like the rest of us here, I want to get to the shallow water equations. So that's about where we are, and thanks for your time.
Questions over here?
I was wondering how to keep the conservation of mass during the transfer from the distortion grid to the regular grid.
Well, there's a couple ways you can do it. You can decide whether you want to conserve we think you can do it better with Voronoi meshes, which is one of the reasons we want to try them. Right now, it doesn't conserve mass exactly, but the error converges like 1 over n. So for the advection test cases, our errors were like right in there with every other group that participated in that workshop. So I think with the Voronoi mesh, the way we do it will conserve mass exactly over the whole sphere. But right now, the mass conservation is a little bit of error at each remeshing.
I was wondering if you could get rid of the mesh at all.
I think you can if you take because what we need is the area, right? And so that's where the Voronoi mesh comes in, because then you can just have a collection of points, but you need somehow to figure out how much vorticity you assign to each particle, and that's the integral. So you need the area, and if you can use a Voronoi algorithm to decide how much area to assign to each point, then you don't need the panels at all.
Any other questions? I was just wondering, how does forgetting about adaptivity for a second, so if you just choose a particular resolution, as I increase the resolution, does the time that I need to remesh change? Does it get
Yes, so the remeshing algorithm is an order n work.
Oh, I don't mean the cost, I mean the frequency at which you need to remesh, does that change?
Oh, no, actually, I think it would decrease. I think the higher resolution meshes stand up better to distortion. So I don't think you need to remesh them as often. But we haven't checked that yet. That's just my guess.
It'll be interesting to see how it scales with the number of points. So the reason you keep these areas is because you want to evaluate the bio-Savart law. So the other kind of vortex methods, there's two options. You can either use these kind of you have to sort of either have the Green's function, which you kind of have to evaluate over all the particles, or there's and so they've got the same problem that you have this order n squared thing. So is this what you're trying to avoid by having this?
That's what the tree code helps. Because either way, it's an n-body simulation problem. The other method is to use the Birkhoff-Rod equations, which use the circulation instead of the vorticity, but it's still then it's a line integral instead of a. But you need lots of contours then to resolve the flow.
Very high shear. Can you imagine a situation where you'd need to remesh every time step? And if so, are there advantages to this over Ale or semi-Lagrangian?
I don't know. I don't. These are singular integrals, and the remeshing introduces interpolation error every time we do it. So I've tried remeshing at every time step just to see, and it doesn't look good.
So if you had very high shear, would it be necessary to remesh?
I don't know. I'm hoping not, but I think we're going to confront that when we get to the shallow water equations, because then we'll have the problem of compressibility too. So not only will there be more shear, but the particles could actually, if we don't remesh often enough, they can get too close, and then the singularity of each integral could become a problem. Because right now we can rely that since the fluid's incompressible, the active particles stay separated from the passive particles, and so that singularity isn't a problem. But if there's compressibility, then the particles can get too close to each other. So we'll have to remesh for that reason too, or use some sort of smoothing parameter.
Well, that's kind of a follow-up question, but wouldn't it make sense to only remesh in those places where you have strong shear and where your cells, because you kind of reset the whole grid. Mm-hmm. That seems like a lot of work if your problem is quite local where the shear is.
Yeah, so you're like if you just need to reconnect the particles in a nice way, and I think that can be done better in the context of Voronoi tessellations, because then you can confine that to a local area. But right now, my data structures rely on everything being a triangle, and that's why I have to do it this way.
I think we better move on to the next speaker, so let's thank Peter again.